Okay, welcome to Extra Notes number 3, where I'm going to go through an example of applying KCL and KVL. So this KVL and KCL are really our only two big rules. Everything that we do pretty much gets traced back to KCL and KVL. They are the only global rules that describe how circuits work. Every circuit must satisfy KVL and KCL everywhere. Every node must have KCL, every loop must have KVL satisfied. So everything else that we do really ties back to KCL and KVL. So learning how to properly apply them is absolutely crucial. And fortunately, there's just a few simple rules. It's fairly systematic. And at this point, you should be focusing on just making sure that for any node you can write the KCL correctly, and for any loop you can write the KVL correctly. In this example, we'll write 2 KVLs and 2 KCLs, and then we'll solve. But the focus really should be on how do I write the KCL correctly and how do I write KVL correctly. It turns out KCL, generally, people don't have much trouble with that. But KVL, even though it's kind of the dual of KCL, for some reason students tend to have more trouble writing KVL than KCL. Now, hopefully I haven't scared you away, but I'll show you the trick. If you do it a systematic way, you'll always get it right. Just a very simple rule that you have to remember. And so here are the rules to remember. So KCL is just the sum of currents entering a node as 0, and so we use a sign convention that if we have an arrow into a node, then we're going to assign a positive sign to that label. So we'll put an arrow into a node and put a name on it, say I1, and so then when we're writing our equation, we will add that current. For every arrow out of the node, we put a name on it. We will subtract that name to have it coming out of the node. So when we're talking about the positive sign and negative sign here, we're not, listen to me carefully, we're not talking about the actual numerical value that we get for the current. We're just talking about the positive sign and negative sign that we use when we write down the sum for our equation. Same thing for KVL. We're going to be going around a loop. So a loop, any closed path. And so for a given circuit, there may be many closed paths that we can write a KVL around. So we pick one closed path and we want to write a KVL around that closed path. And what we're going to do is systematically, just as a convention, always go clockwise. Doesn't really matter as long as we just stay consistent and we're just writing these rules down so that you'll have a very systematic way to do this. So we're going to just add up. So that adding up will require some positives and negatives. We're going to add up the voltages, and here we're not adding up numbers, we're adding up symbols that represent the voltages that we're ultimately wanting to find. So we don't necessarily know what those numbers are, so we're not adding up numbers, we're adding up symbols. And so we have to have a convention for when we add the symbol and when we subtract the symbol. So we will assign a positive sign. And again, this is not the numerical sign, but whether we're adding or subtracting to our sum, we'll use a positive sign to the voltage across an element if the plus side of that voltage is encountered first. So notice up here we have an arrow direction and we have a sign relevant to that arrow direction, and down here we have a plus minus orientation and we have a plus minus connected to that orientation. So if we go into the plus side, we will add it. If we go into the negative side, we will subtract it. And so that's very easy to remember. And then here's my suggestion. The book and the videos created by the authors of the book, they get tricky right away. They jump right into using Ohm's law to write out the equations in terms of currents and resistors. And I'm going to suggest that you avoid doing that. Yeah, it makes you go through an extra step, but we won't always be having resistors in our circuits. And so it's good to get used to just writing the KVL without worrying about how the voltage gets linked to a current. We'll do that soon enough when we get into loop and mesh and nodal. We'll do that. But I'd like you to kind of just hang for a while and learn how to write out the equations first without using the specific device law, so that you can see that what you're really doing is just adding up voltages when you go around a loop. This is for KVL in particular. And then that we are substituting in for those voltages using Ohm's law in particular, because we have resistors. But we might have something entirely different there that we would need a different VI rule for. So this helps you keep track of the fact that the KVL and the KCL are systematic circuit rules, and then Ohm's law is just a device rule for the specific devices that we're currently talking. So here's an example. This is out of the textbook, so you can follow along with it with what's there. It's in the notes for the textbook that I provided. And I could have picked one that was not in the book, but I chose one because I chose this one because it was in the book, so you have access to that solution. What I'm going to do is provide through the video a little more discussion and explanation as to why we do things the way that we do it. So one of the features of this particular example is that we have a dependent voltage source, and we'll see here that that really doesn't bother us at all. We can still write our KVL and KCL. And our goal here is to find the power in this 12 ohm resistor. Now, we just happen to apply KVL and KCL to answer that. KVL and KCL could be applied to answer other things in this problem. So often we're trying to solve for all the currents or all the voltages in a particular circuit. Or sometimes we just want one particular circuit characteristic. In this case, it's power of one particular resistor. So that's what we want to do. And so the first thing we're going to need to do, since we're told to apply KVL and KCL, we need to identify some loops and a node. So if we go to the next slide, we'll see. If we go to the next slide, we'll see here the same circuit, just extended a little bit vertically so that we could fit a little bit more information in there. And we've labeled a few things here. So we've labeled loop 1 here. That's following this path. And let me get rid of that. And then we have loop 2 that's following this path. And one thing that we'll notice, and this will come into play when we get more into our mesh analysis, notice that there is an element in common between loop 1 and loop 2. So this 8 ohm resistor actually plays a role in both of those. But it doesn't really matter. That's just the nature of the circuit, so that's not something to worry about. So we've got 2 loops. We could actually have defined a third loop, which is around the outside, and we could use that. But the problem says to use KCL in addition to KVL. So we'll need to identify some nodes. So we have one node there, and we have a second node there. So you might think that we could write two different KCL equations here. And we'll see in just a little bit that that's not actually true at all, that we can only write one independent KCL. Now, it is true that there are some other nodes here. There's a node here and there's a node there. Those are simple nodes where there aren't three or more components coming together. So node 1 and node 2 are what the book calls extraordinary nodes, and those are the ones that we're really interested in. So the first thing we're going to do is write KVL around loop 1. And so just remember our rules. We're going to go clockwise, and that's just convention. There's nothing special about clockwise. That's just the convention that we've chosen. And remember that we are going to write our KVL not like the book's been doing it in terms of immediately using Ohm's law, but rather in terms of general voltages. So before we do our KVL, let's identify some voltages here. So if we put a plus and a minus and call this V1, notice that I did that according to passive sign convention, which will allow us to apply Ohm's law properly. And then we'll put a plus and a minus here, and we'll call that V3, and we'll put a plus and a minus here, and we'll call that V2. So these are just names and really arbitrary sign conventions, but since the book has already applied currents into and out of node 1, we will apply our voltages so that they are their plus minus sign convention is satisfying passive sign convention for the currents that were already assigned. So now we're all set. We've got our arbitrary voltages named and signed. We've got our currents named and directioned, and we're all ready to go to write KVL around loop 1. So we're going to start. It doesn't really matter where we start, but we'll start down here at the lower left-hand corner. We're going to go clockwise. And so as we go, the first thing we run into as we go clockwise around this is we run into the 20-volt source. It's a voltage source, so it's a 20-volt voltage source, and we're going into the negative side of it. So our rule is that it contributes as a negative term to our sum. We do know the actual value of this, so it will be negative 20. So there's the first term of our KVL sum. Then we continue up. We hit the 4 ohm resistor up at the top. Notice that we are going into the positive sign of our convention there. So this is going to add. And we're going to, as I suggested, just leave it as V1 and not worry about applying Ohm's law at this point. Just keep everything stripped down to the bare essence of this. So we get plus V1. We continue around loop 1. We're now going down through the 8 ohm resistor, and we see that we enter that on the plus side. So we're going to have plus V2. And then we come down and we're back to where we started. And so we've summed up all the voltages with the proper signs around our loop, and so that must be equal to 0. So there's our first KVL around loop 1. And then part B of that first step is to now exploit the device rule. And since we have just resistors in here, aside from our voltage sources, we just use Ohm's law. So V1, with the way that we have the sign convention set up, we've got current, the assumed direction for I1 going into the assumed positive side of V1. So V1 now will just be equal to I1 times 4. So we can replace that. So we'll have minus 20 plus 4I1. Now we go to V2. Again, we see that we've set this up. Doesn't matter whether we did or didn't. If we didn't, we'll just have to include an appropriate negative sign. But because we have I2's arrow going into V2's plus, then we know that we have passive sign convention satisfied, and we will have V2 is equal to plus I2 times 8. So we're adding V2, and it's plus 8 times I2. And that's equal to 0. So there is the first equation that the book would just jump immediately to. And like I said, I don't like jumping immediately to this equation, at least not right off the bat. All right, now we're going to write KVL around loop 2. We will start down here. We'll start at node 2, and we'll go clockwise around. So the first thing that we do is we hit this 8 ohm resistor, and we've labeled the voltage across that as V2, and notice that we're entering on the negative side, so we will get a negative V2 as our first term. We go up, we go through the 12 ohm resistor. Notice that we are entering along our clockwise route. We're entering into the positive side of that, so we will have plus V3. And then we're going down. Now, this is a dependent voltage source, but it doesn't matter. We treat it just like anything else. We're going into the negative side, so it'll be subtracted. And what is the value of that voltage source? Well, it's 8 times I1. So that we can write out immediately, just following the rule. And then we're back to node 2, and so we've completed our loop, so that's equal to 0. And so now we have 2 resistors in that loop for which we can exploit Ohm's law, the device rule for each of those devices. And again, we see that we have things set up so that I2 arrow goes into V2 plus sign. So V2 itself is just equal to I2 times 8, or 8I2. But because we have the negative V2, we'll still have the negative sign there. That's from the KVL direction that we were going. And then V2 itself is positive 8 times I2. So we have positive 8 times I2. Then we go to V3. Our route around the loop gave us a positive V3. The arrow for I3 is going into the positive sign of V3. Therefore, V3 is equal to plus 12 I3. So we had the plus from the KVL direction, and then times plus 12 times I3. And then we have minus 8I1 for the dependent source, and we set that equal to 0. So we now have 2 equations, 1 and 2. Notice that we have 3 unknowns. We have I1, we have I2, and we have I3. So we have 2 equations in 3 unknowns. That means we need 1 more equation, and that's why we need to do a KCL. Okay, but we've been told to do a KCL. So we're going to do KCL at node 1. So we have I1 in, and we have I2 and I3 out. So we could say I1 minus I2 minus I3 is equal to 0. That's one way to say it. Or we could say the ins must equal the outs. So I1 must be equal to I2 plus I3. And that's how we'll write it here. I1 is equal to I2 plus I3. And notice that I'm saying here that KCL at node 2 is going to be exactly the same. Notice that if we trace I1 here, we can trace it all the way back over to here. So I1 is actually coming out of node 2. I2 is going into node 2, and I3 is going into node 2. Just remember that we have the same current everywhere through that branch. So we have I1 is the out and I2 plus I3 is the in, so we would get the same exact equation. So even though it looks like we have two nodes that we could write two different KCL equations for, that's not actually true. Okay, so we've got our KCL written, and so now we've got three equations in three unknowns, and we're ready to proceed. The next slide here shows how we can solve these equations. So I've just rewritten the three equations here exactly as we had them, and then I've manipulated them to just get them into a form that makes it a little bit easier to solve using a numerical technique. And what I've done is I've gotten all of the currents over on one side and any constant over on the other side. So I've swung this minus 20 over to the other side and made it a plus 20, just leaving behind the 4I1 plus 8I2. I didn't do anything with this one. I did just reorder them in the order of I1, I2, and I3, just to make it a little easier to see the structure. And then finally, this one, I swung the I2 plus I3 over to the other side, so I get I1 minus I2 minus I3 is equal to 0. So now I have three equations in kind of a standard form where I have something I1 plus something I2 plus something I3 equals some constant. And I have three different equations of that form. Now, there are a lot of different ways that you can solve this. One of my favorite websites is this wolframalpha.com. If you've not gone there, try it out. When you get there, it will give you options for finding answers in a lot of different things, and mathematics is just one of those. So there are ways to select mathematics and then sub-areas within mathematics, but you can also just type directly into, up at the top there will be a box that kind of looks like this, and you can type directly into it. And so you can see here that what I've done is I separated by commas, I've entered the three different equations here that correspond to these, and I just used X, Y, and Z to just make it a little bit easier to type it in rather than I1, I2, and I3. So you just literally type those in. You type them in separated by commas. So let me just get rid of this so that you can see those commas. So here's a comma, and there's a comma. So I have three equations that are separated by commas, and then I literally just hit enter, and it then spins for a little while, and it comes back and it gives me the solution. I1 is equal to 25/7, I2 is equal to 5/7, and I3 is equal to 20/7. And remember the units of each of those would be amps. So that's one way, and my focus in this course is not on whether you can solve systems of linear equations. That's not what makes a good engineer. What makes a good engineer is whether you can see a circuit, whether you can understand what the rules are that govern its behavior, whether you can write down the appropriate models that govern that behavior, and whether you can find some way, numerical or analytical, analytical meaning solving it by hand, to get your answer. So on the homework, you're free to use calculator, or Wolfram Alpha, MATLAB, Mathematica, whatever you want. On the exams, I'll make them simple enough that you can do it by simple substitution, which I'll show you for this next on the next slide. But you're also free to use your calculator to solve a system of equations. Just tell me on your solution that you used your calculator to find it. Obviously, I'll expect that you've used it correctly to find the solution, and I'll hold you to being able to do it correctly. But that using a calculator to solve that is perfectly fine in my mind for engineering. Okay, so suppose we did want to solve this particular problem by hand. So here's our same box with the rearranged equations in kind of the standard form with I1, I2, and I3 with coefficients on the left equal to some constant. And we're just going to try to isolate this to get this to a point where we can isolate just a single variable. And so there's certain rules, and you've probably learned these rules at some point, that allow you to add and subtract equations, and multiples of equations can be added and subtracted and substituted back in and remanipulated and so forth. So there are systematic ways to do this. Maybe you've done like Gaussian elimination or something like that. But again, I'm not stressing that you have to demonstrate your chops on those things. So anyway, we start with the bottom equation, which here I've just rewritten as I3 is equal to I1 minus I2. And so now I can substitute this in for I3, and I get just an equation in terms of I1 and I2. So after substituting that in, grouping like terms, I get something that looks like that. And now I'm going to take that equation together with the top one, and noticing that 4I1 shows up in both places, I can eliminate the I1 variable by subtracting one equation from the other. So I'm going to take the top one that I show here and subtract the bottom one from it. When I do that, those cancel. I get 8I2 minus a negative 20I2, which gives me 28I2, and I get 20 minus 0 is 20. Let me clear some of this stuff off here. Get a little busy after a while. And now I can solve for I2 just by dividing 20 by 28, and simplifying that fraction gives me that I2 is equal to 5/7 amps. And now I can go back up to this equation if I want. I could go back to my original equation here if I wanted to, and I can substitute in that value of I2, which I've done here, and now I have something that is just in terms of I1 alone, and so I can solve for I1, and I find out that it's 25/7 amps. Then I go back to that I3 is just the difference between I1 and I2. I now know I1 and I2, so I can subtract those, and I get that I3 is equal to 20/7. And then finally, remember that this problem is actually asking us to solve for the current through the 12 ohm resistor, or I'm sorry, the power dissipated by that 12 ohm resistor. And so the current that goes through that resistor is I3, so we use our formula for power, that's current squared times resistance. So I3 is 20/7, so I put in 20/7 squared times 12 ohms, gives me 97.96 watts. So I'll give you a hint or some insight. That's an awful lot of wattage for a circuit. Typically, when you're dealing with circuits inside like iPhones and stereos and things like that, you will not encounter such large wattages. In fact, the resistors that you bought for the labs are quarter-watt resistors. That means the maximum power they can safely dissipate is 1/4 watt. But it's pretty remarkable that just with something like 20 volts of voltage, and then we end up with a dependent source that is 8 times I1. Our I1 was 25/7, so we're at about 20. just a little bit more than 25 volts for that voltage source. So we've got 20 volt and 25 volt sources, and we end up with close to 100 watts being dissipated by this resistor. Largely that's because it's such a small resistance, 12 ohms. Now you might say, yeah, but wouldn't we want a large resistance to make this power as large as possible? Well, the larger we make that resistor, we're likely to get much less current through it. So you have to remember that changing the resistor value will change the current as well. So bottom line is that when you're using larger resistors like 1K, 2K, 10K, 100K, with voltages of 5s and 10s, you're going to be dissipating much, much less power. So I just want to make a comment here. This is our last slide, but notice what I did at the end of my solution. I didn't just blindly write down a number and then just turn it in to the professor, because that's what you're used to doing. You need to learn to become an engineer. When you're out in the real world, it's rare that things are really boiled down to, here's a single number, and that's all that anybody cares about. And before you go giving your supervisor or your mentor your solution, I would strongly recommend that you think about your solution and see, does it make sense before you start showing it to other people? Because if you start giving them results and then they discover, oh, look, this isn't quite right, or wow, you really thought that that could be the answer? It makes absolutely no sense. There's no possible way. You are now undermining your coworkers' confidence in your ability. So the last thing that you do when you are solving a problem is you kind of go back and you make sense of it. You ask yourself, are these values that I got reasonable? I remember in graduate school being given a homework problem, and I must have solved this probably 5 or 6 times. I kept checking it. It was a problem that involved an electric motor, and they showed us a little picture of the electric motor, and it looked really small. And we were supposed to find the amount of torque that this motor was providing. And, I came up with something like, 10,000 foot-pounds of torque. And I thought, that little motor, it was like a motor that you could hold in your hand. That little motor, there's no way it's going to put out 10,000 foot-pounds of torque. So I kept checking, and I couldn't find the answer. I couldn't find the reason why I was getting such a large number. So I finally submitted my solution, but I wrote a little comment after I wrote down my 10,000 foot-pounds of torque answer, and I said, I just can't believe that this little motor would put out 10,000 foot-pounds of torque. I've double-checked, triple-checked, quadruple-checked. I cannot find anything that I've done wrong, but I doubt this answer. And I got back a wonderful little note from the professor saying, at least there was one thinking engineer in the class. It turned out that he had given us the wrong conversion factor, so I had been fed bad information. But I'll tell you what, my one little comment there earned me much more than praise from this professor. It earned me the respect of that professor. And in my early years in graduate school, that professor really then opened up a lot of doors for me. And helped me succeed in ways that he probably wouldn't have if I, hadn't earned his respect that way. So, moral of the story, every time you do a problem, double check it. Make sure it makes sense. Ask yourself, why does this work this way? Ask yourself, why is it big? Why is it small? What is it that's driving this to be this way? The more you ask questions like that, the better an engineer you'll ultimately be. And hey, that's the actual goal of all this work that you're doing this summer, as well as in your regular semesters. All right, so we'll stop there, and hopefully this provides you with some good insight.